Hello everyone. Today we are going to discuss about solutions chapter of class 12. This was chapter number 2 previously. Now it is chapter number 1 after the deletion of solid state chapter. Solution means it contains solute and solvent. Now in our syllabus we have binary solutions containing two components only. Binary solution contains two components, out of which one is solute, the other is the solvent. The type of solvent and the type of solute can be of all the different phases. But keep in mind that the phase of the solvent decides the type of the solution. Like that, we will see certain examples. We are going to see laws pertaining to the vapor pressure of a solution. Whenever we have a solution kept in a container, the empty space above the container contains vapors of the solution or vapors of the solvent that is kept in the container. Or I can say vapors of the liquid kept in the container. Liquids only doesn't exert pressure. Gases also exerts pressure. So let us see in details all these theories, all these practical observations. Hello everyone. Today's session is on solutions. First, we need to know what is a solution. A solution is a homogeneous mixture made of two or more substances. If it contains only two components, then such a solution is known as a binary solution. Only two component means the solution is a binary solution. Now, solutions can be a solid solution, liquid solution, and gaseous solution. I have already said in the introduction part that depending on the type of the solvent, you can categorize types of solution into solid solution, gaseous, and liquid. There are 9 types we can see, 3 here, 3 here, and 3 more here. So, out of these, the most commonly used are gas in liquid, liquid in liquid, solid in liquid solution. The examples are given over here in the tabular form. Now these examples can be picked up in exam and you may be asked to identify what is the type of the solution, what is the phase of the solute and the solvent. So did you notice that amalgam is a liquid in solid solution. So it is an example of solid solution. There are certain examples like copper dissolved in gold. It is an example of solid in solid solution. Okay. After this, we have solid in liquid solution. Discussion starts with that type of solution because I said there are 3 things that we are going to discuss. Gas in liquid, liquid in liquid, solid in liquid. So we will discuss it in the reverse order. Solid in liquid, liquid in liquid, and then gas in liquid. The first thing is solid in liquid solution. So of course it's a homogeneous solution where the solid is your solute and solutes are given by B conventionally and solvent is your liquid and solvent is given by conventionally A. Example of such type of solution is sugar in water, salt in water. Now types of solution can also be dilute solution and concentrated solution. In dilute solution, with respect to the solute, we have large amount of solvent. In concentrated solution, the amount of solute is greater with respect to the amount of solvent. Next, another type of solution is unsaturated, saturated and supersaturated solution. All these 3 types of solution actually depends on the relative amount of the solute present in the solvent at a given temperature. If I say unsaturated solution, that means it's yet to get saturated. That means more amount of solute can be dissolved at a given temperature. So you can dissolve more solute at a given temperature. Saturated solution means whatever is the maximum amount of solute that can be dissolved in a particular amount of solvent at a given temperature, it is already present. So maximum amount of solute that can be dissolved at a given temperature is already present. Supersaturated means more than saturated. And obviously, at a given temperature means you need to do something with that. What do you need to do? Heating the solvent to dissolve extra solute, then slowly cooling it down carefully. This actually is the process of crystallization. Now, these solutions are unstable. Why? Because whenever you disturb such a solution, you shake it or you add any crystal, that can cause the excess solute to suddenly crystallize. So they are not stable solution. So next, what is solubility of a solute in a given amount of solvent? Solubility is the maximum amount of solute that can be dissolved in a given amount of solvent, of course at a particular temperature and pressure, in order to form a homogeneous solution. That is known as solubility. So when I discuss them separately for solid in liquid, that means how much of the solid solute can be dissolved in a particular amount of the solvent. So I have taken it as per 100 gram of the solvent. So it tells how much of the solid can be dissolved in a liquid solvent. And the mass of that liquid is kept as fixed 100 gram at a particular temperature. Example, 36 gram of NaCl per 100 gram of water at 25 degrees Celsius. Now, what are the factors that affect the solubility of solid in liquid? There are many factors, out of which there are the three main factors. Nature of the solute and the solvent. Generally, we have heard like dissolves like. What is this like dissolving like? A polar solvent dissolves dissolves all polar solute. Non-polar solvent will dissolve non-polar solutes. Why? You know what? Why does at all a solubility occur? If I say there were previously existing interaction between the solvent particles AA and there were previously existing interaction between the solute particles, which is denoted by BB, then if a solute is dissolving in a solvent, new interaction develops AB interaction. Now this AB interaction should be stronger and should liberate more amount of energy in order to overcome the previously existing solvent to solvent or solute to solute interaction. If this can happen, then the solutes will be dissolving, having a good solubility in any solvent. So, next is temperature. For most of the cases, it is seen that solubility increases with temperature. But it actually depends on what type of reaction it is. If the solubility process is endothermic, then for those solubility processes, the solubility will increase with increase in temperature. Solubility increases with increase in temperature. But if it is exothermic, then the solubility decreases with increase in temperature. There is inverse relation. But generally we say solubility increases with temperature because most of the cases are endothermic cases. But some more salts like cerium sulfate solubility decrease with temperature. So obviously the process of solubility of cerium salt Maybe exothermic. Of course, it's exothermic. Next is pressure is one of the factor, but keep in mind solids are incompressible. So it hardly is affected by change in pressure. So very little effect, negligible effect. Why? Because solids are incompressible. For that reason, change in pressure hardly affects the solubility of solids in liquids. Now, solid, when I'm talking about, I have to talk about something which is known as lattice enthalpy, lattice energy. So, there is a competition between solvation enthalpy, energy released due to this AB interaction. The energy that is released is your solvation enthalpy. That's your change in solvation enthalpy. Okay, so this solvation enthalpy and lattice enthalpy has close relation. What is the relation? Solvation enthalpy, if it is high, that means more amount of energy is released on account of solvation, and that is a stabilizing factor that causes more solubility. So high solvation enthalpy means more energy released, solubility is increased. And why more energy is released? Because AB interaction is a favorable interaction, then only more energy is released. Now, high lattice enthalpy means strong ionic bonds existing, and you need huge amount of energy to break those existing bonds. That causes lower solubility. In order to cause greater solubility, a balance should be there between the two, and the solvation enthalpy should be greater than the lattice enthalpy. That means the energy released on account of the newly developed AB interaction should be greater and should be sufficient in order to break the existing lattice enthalpy. If the ions are coming to the solution by breaking of the crystal lattice, then only the favorable interaction can take place. So this is the example of NaCl, lattice enthalpy moderate, hydration enthalpy high, solubility is high. Hydration enthalpy should be high enough and higher than the lattice enthalpy, then only the solubility will be high. But if the lattice enthalpy is high and hydration enthalpy is not enough, then solubility is low. So always the comparison between lattice enthalpy and the solvation enthalpy, it judges what type of solubility will be there between the solute and the solvent particles. Next, moving on to the solubility of liquid in liquid solutions. This is the other one. When two liquids are mixed, they can form a homogeneous or uniform solution depending on what type of interaction exists between the two. So it's always not that the one liquid mixes with the other. Examples are miscible liquids where ethanol, water. What is the cause of this mixing? Intermolecular hydrogen bonding. The cause of this mixing is intermolecular hydrogen bonding between the ethanol and water. So please remember that a liquid solvent and a liquid solute will be dissolving, will be miscible if this AB interaction is a favorable interaction energetically. That means energy should be released due to the interaction, and that will be causing miscibility. Next, immiscible liquids means the interaction is not favorable. They are not mixing. Oil in water, they do not mix. They form two separate layers. Partially miscible means phenol in water is capable of forming hydrogen bonding, but phenol has a high I will say large hydrophobic part. This is the hydrophobic part of phenol, for which the solubility is less. Hydrophobic part is large, for which the intermolecular hydrogen bonding will be weak. Intermolecular hydrogen bonding with H2O will be weak. So that causes slight solubility of phenol in water in comparison to alcohols in water. Alcohols are largely soluble in water. Remember, lower alcohols will be more soluble than higher alcohols, because as the mass increases, the solubility will decrease. Van der Waals interaction increases. Next, फैक्टर्स अफेक्टिंग सॉल्युबिलिटी ऑफ लिक्विड इन लिक्विड में क्या है? एक और थिंग, दैट इज टाइप ऑफ द लिक्विड. पोलर लिक्विड विल बी dissolving in polar solvent, non-polar liquid will be dissolving in non-polar solvent. That is type of solute and type of solvent, just like the previous case. Next, coming to, see, example was given to you as well. Water and ethanol, both are polar and so both are miscible. Water and hexane. Water is a polar solvent, but hexane is non-polar solvent, so immiscible. Next, going to temperature. In general, increasing temperature increases the solubility. Of course, because we are considering that most of the solubility are endothermic in nature. For liquid-liquid system, effect is usually less dramatic compared to solid in liquid. मतलब ज्यादातर changes नहीं होते हैं, dramatic changes नहीं होते हैं, drastic changes नहीं होते हैं. Hydrogen bonding, I have already told you, water and alcohol forms intermolecular hydrogen bonding, which gives a stronger interaction between solute to solvent, and so it is miscible. It increases the solubility. Intermolecular forces, type of interaction. If the interaction is a stabilizing interaction, that is interaction between solute to solvent is a stabilizing interaction, solubility will be more. That is stronger attractive forces between unlike molecules. Unlike molecules means AB interaction. Then higher is the solubility. This is a summation of whatever I have said. Nature of the liquid, temperature, hydrogen bonding and intermolecular forces. Moving on to solubility of gases in liquids. Gas भी soluble होते हैं ना liquids में. तो solubility of gas in liquid actually is the amount of the gas that can be dissolved in a given volume of liquid at a specific temperature and pressure. Common examples are aerated drinks, carbonated drinks, CO2 dissolved in soft drinks, oxygen dissolved in water for aquatic life. Fishes get that respiration, they respire from that dissolved oxygen. And what are the factors that affect the solubility of gases in liquids? Mainly the pressure. And here we see Henry's law, which states that the solubility of gas in a liquid is directly proportional to the pressure of the gas above the liquid at a constant temperature. See, whenever a liquid is kept in any container, suppose this is the liquid, this empty space is actually having vapors of the liquid, which later on we will see is called the vapor pressure. Now, if I talk about dissolving any component, a gas, a gaseous solute in a liquid solvent, then how much of the solute can be dissolved? It depends on the gas pressure above the liquid. That is the partial pressure of the gas in the vapor phase. So this is the partial pressure of the gas in the vapor phase, and that is proportional to the mole fraction of the gas in the solution, in the liquid phase, in the solution phase, because you're talking about A plus B. That is, in this liquid, B is dissolved. The gas is already dissolved in the liquid. So what is the mole fraction of the gas in the liquid? That is X. If X is greater, then the partial pressure that it will exert will also be greater. So P is the partial pressure is proportional to X, And as per Henry, P is equal to KH into X, where KH is Henry's law constant. Remember always that Henry's law constant has an inverse relation to the solubility. A solubility of a gas will be greater if its KH value is less. So examples are soft drinks, I have already told you. Temperature, as temperature increases, solubility of the gas will decrease because gas particles are free to move. When you increase the temperature, you actually increase the kinetic energy of the gas particles, which helps to overcome the surface and escape out. Therefore, cold water holds more gas than warm water, and aquatic animals survive better in cool lakes because of more dissolved oxygen in it. Next is nature of gas and solvent. Gases that can form interaction, stabilizing interaction, hydrogen bonding with the solvent, that will be more soluble. Again, I will say nature of the gas means polarity. NH3, HCl, they dissolve better in water because of their polar nature, also because of the capability, wherever there is capability of forming hydrogen bonding, of course, not everywhere. So oxygen, oxygen, fluorine, nitrogen, they are capable of forming hydrogen bonding. Non-polar gases like N2 and O2, they are less soluble because in water, because their polarity is less. Again, this is a summary table of whatever I have told you just now. Application of Henry's law. Carbonated beverages, CO2 is dissolved in drinks under high pressure. And when you see that when you open the lid, when you open the bottles of the cold drinks, what happens? A fizz happens. This fizzing out is due to the sudden change in the pressure. The CO2 was compressed. And when you open the lid, when you open the bottle, there is sudden change of pressure and the CO2 escapes. And in scuba diving, deep sea scuba diving, under high pressure, more nitrogen dissolves in the diver's blood. And when the diver comes to the surface too fast, what will happen? Suddenly there will be variation of this pressure of nitrogen that is dissolved in the blood, variation of the pressure, and the nitrogen comes out suddenly causing bubbles. And bubbles in the actually obstructs the blood flow, causes bends. For that reason, divers use oxygen and helium mixtures because helium is less soluble in the bloodstream than nitrogen. Respiration is often very difficult at high altitudes. At high altitudes, people carry oxygen cylinders. Why? Because at high altitudes, there is less, in the atmosphere becomes thinner and thinner, and there is less oxygen in the atmosphere. And since the atmospheric pressure is less, the oxygen dissolved in the blood also becomes less, and people face breathing difficulty, and they actually lose the ability of thinking and coordination and correlation. And this phenomena, this medical condition is known as anoxia. So they carry oxygen cylinders. We see Henry's law application in the gas exchange in the lungs. The diffusion of the gases O2 and CO2 in and out of blood is governed by the partial pressures applicable, whatever we have seen in the Henry's law. But Henry's law has certain limitations as well. You know what happens? This is applicable at low pressure, not at high pressure. They deviate from the behavior. It is applicable for ideal solution. It deviates if the gases reacts chemically with the solvent. It does not apply to gases that dissociate or react with the solvent. So, it is also affected by temperature. Why? Because we have said at a constant temperature this thing is happening. So the law is valid only at a constant temperature. This is something which I have already told you, relationship between KH and solubility. There is inverse relationship. And these are the numericals in text question based on Henry's law. H2S, a toxic gas with rotten egg-like smell, is usually used in qualitative analysis, group analysis. You will see in your practicals, H2S is used. If the solubility of H2S in water is given, this is the solubility, calculate Henry's law constant, Kh you are supposed to find. So, this is the procedure. See, solubility means this is given in molality, means mole per kg of the solvent. So, this many mole of H2S is dissolved in per kg means 1000 gram of the solvent. So, you find out how many moles of it is dissolved. So, number of moles of H2O, this is the number of moles of water. H2O, number of moles of water. Given mass by molar mass, that is number of moles. Number of moles means given mass by molar mass. So, of water if I say, then it is NaWa by Ma, that is this. Of H2S, that is the solute. So, Nb is equal to Wb by Mb. And mass over here, we need to see mole fraction, of course, because the formula is P is equal to Kh into the mole fraction of the solute. So, mole fraction of the solute means number of moles of H2S divided by number of moles of H2S plus H2O. We have done in class 11. So, here is the mole fraction. Place the value and get the value of Kh. You can get the entire write-up, you can get the entire notes in the description part of the video. Please go through and get access to it. This is another numerical of in text. Henry's law constant Kh is given at a particular temperature. Calculate the quantity of CO2, that means Wb, in 500 ml of soda water when packed under 2.5 atmosphere CO2 pressure at 298 at the same temperature. So partial pressure is this, Kh is this, you apply Henry's law and you get mole fraction. Mass you have to calculate because you have to place it in the mole fraction relation now. So mass of water you got, number of moles of water, mass by molar mass, and you get the number of moles. Place it in the mole fraction formula and calculate the number of moles of CO2. And just now I told you number of moles is equal to mass by given molar mass. So you need to find out mass. If you multiply the number of moles by the molar mass of CO2, you will get the mass. Thank you all of you for being partners in this session. Let us go forward in the solutions chapter in the next sessions. Till then, bye.